The concept of a function will be at the foundation of almost everything we do in calculus, so it's very important that we understand what functions are and how to use them. So, what is a function? A function is just a relationship between variables. If I have an equation like y equals 2x plus 1, then that represents a relationship between x and y. For example, maybe x is how much candy I order on the internet, maybe in pounds, and y equals the price, how much it costs. According to this formula, maybe they're charging $2 per pound of candy and then plus an extra $1 for shipping regardless. So the price in dollars, I should say. Once you have that relationship or that rule, then you can figure out y from the value of x. In this situation, and almost always for our purposes, x is the independent variable. I get to choose x. I get to decide how much candy I'm going to order. And then the value of y depends on x. So y is the dependent variable. Another way to say that y depends on x is to say that y is a function of x. Y is a function of x. So that's the same as saying y depends on x. We indicate that by writing function notation, y equals f of x. Y is a function of x. That's what that notation means. This notation can be confusing because it almost looks like multiplication. It looks like f times x, right? But it's not. F of x here is sort of one symbol. It's the dependent variable. It's y. Y equals f of x. So we could write y equals 2x plus 1, or we could write f of x equals 2x plus 1, because y equals f of x. The x inside the brackets tells you what the input variable is. It tells you what you're going to put into this function. F of x equals 2x plus 1 shows you that you have a function, and if you put x into it, then you get 2 times x plus 1 out of it. F of 3 would be 2 times 3 plus 1 equals 7. So if I ordered 3 pounds of candy, it's going to cost me $7. F of 3 would be the output of the function when you put 3 into it. It might be helpful to think of a function not only as a relationship, but as a machine. It takes an input x and gives you an output y. If I put 3 into the machine, that is f of x equals 2x plus 1, I put in 3, I get out 7. Suppose I have a different function. Suppose I have the squaring function, f of x equals x squared. So that's the same as y equals x squared. If I put in 2 into this machine, it squares that input and outputs 4. If I put in a -1, it outputs f of -1, which is -1 plugged in where the x is, so -1 squared, which is 1. If I put in a heart, it outputs heart squared. If I put in the letter a, then I get back a squared. If I put in a plus b, then I get a plus b all squared, whatever a plus b might be. You can have a more complex relationship between x and y, like you could have f of x equals, and then the x appears multiple times, like maybe x plus 1 divided by x. And it's still a function of x because the output depends on x. It just happens to use the input in more than one place. So now if I want, say, f of 1, then I have to say 1 plus 1 over 1. So I put the 1 in 2 different places. It's important to note that the specific letters f, x, y don't actually matter. The convention is to use x and y for the independent and dependent variable, and the letter f to indicate the function. But I could write f of q equals q squared. And that represents the squaring function. It's the same relationship, the same function, the same machine. If I put a 2 into this machine, I get a 4. I could also write g of x equals x squared, or g of w equals w squared. And that's all the same relationship between dependent and independent variable. These are all the same function. Most often, if we're using a variable other than x, it'll be the variable t, and we'll be in a real world problem where the independent variable is time. So we could have s of t equals t squared. That would be a common thing to see as well.